Hi AP Chemistry class, Mr. Mellinger, and this is the assignment for day 18, assigned on Friday, February 22nd, right after the exam, and it's due on Monday morning. Now, we didn't spend a lot of time on this, but I'd like you to get this assignment done. It's about 6 problems. You can do these in about an hour and do them along with me. So this is limiting reactants. And the concept of limiting reactants is, if you took an equation that looks like this, and it says you need 2 moles of aluminum for every 6 moles of hydrochloric acid to make this reaction go through. Or a more general way to look at this is you need 3 times as much hydrochloric acid as you have aluminum, because 6 to 2 is a 3 to 1 ratio. So you need 3 times as much of this as this. So if this number were 10, this number would have to be 30. If this number for aluminum was 60, then the number for hydrochloric acid would have to be 3 times that, or 180. So that's what this relationship is saying. It's the ratio of how many moles of each chemical you need to make this reaction work. Well, in the real world, you're not usually given exactly, in the case of this reaction, a 3 to 1 ratio. You might be given 10 times as much hydrochloric acid as aluminum. That means the aluminum is going to run out faster than the hydrochloric acid, and then the reaction comes to an end because you no longer have enough of one of the reactants. Okay, so I'm going to show you how to do this, and you'll see different ways or different approaches to this problem, or they look different, but they're all fundamentally the same, is that you have to run the reaction twice. And what you have to do is run the reaction once, assuming that you have all aluminum, and then run the reaction that you use up all the aluminum you were given. And then you run the reaction a second time, assuming that you use up all of the hydrochloric acid that you were given. And that's this row down here. And then you see which of those reactions could actually work, given the amount of the other reactant you were given. So the first thing we need to do is figure out our molar masses. Okay. Now be sure if this correction is not made on the sheet that you have, be sure it's corrected. I may have had the wrong elements here, but it should be aluminum and hydrochloric acid. All we're interested in are the reactants, not the products over here. Okay. Okay, so continuing on with the first problem in your problem set, we're going to work the reaction in 2 different ways. First of all, we're given the number of grams of aluminum that we're provided with and the number of grams of hydrochloric acid we're provided with. Remember that chemical equations only work in moles. They don't work in terms of grams. So you need to use your molar mass conversions to convert from grams to moles. Okay, so we're back. I wanted to do something to save us some time on this video. So you have the molar mass conversions up here for aluminum and hydrochloric acid. Again, it's how many moles. You get this straight off the periodic table by adding the elements H and Cl, and for aluminum it's just purely straight off the periodic table, 26.98. Then remember that chemical equations deal in moles, we deal in grams, so you need to make the conversion from the number of grams of aluminum you were given into how many moles that is. So hopefully by now this is very natural and second nature to you. If it's not, you need to come see me because it's getting to be a critical time that you have to be able to do this easily. So we have 36.4 grams of aluminum we were given. The molar mass conversion right here is telling us the relationship. You need grams to cancel out on the bottom and on the top here so that you end up with moles. That way we can put it into the chemical equation. And we end up with 1.35 moles of aluminum. Doing the same thing for hydrochloric acid, we're given 4.7 grams of hydrochloric acid. We use the molar mass conversion. So it's moles on top, grams on the bottom, because you need grams to cancel out on top and bottom there. And you end up with moles of HCl, it's 0.13. Okay, now we're going to get into how do you do these limiting reactant problems. First of all, this is all of the aluminum we are given right here, 1.35 moles. So this is our all aluminum reaction. So in the all aluminum row, directly beneath aluminum, we're going to write 1.35. And this is moles. Okay, I'm going to circle that because that's an amount we know we have. We were given that amount based on the grams we were given and the conversion. We know we have that many moles. Now, what if we run the reaction so that all the hydrochloric acid is used? So this is a second reaction. We're running the same reaction 2 times. We're going to try to use all the hydrochloric acid. Okay, so we have 0.13 moles of hydrochloric acid. So here in the hydrochloric acid column and in the row, all hydrochloric acid, we're going to put 0.13 moles. All right, and we're going to circle that because that's an actual amount we have. Now we have to figure out these two boxes. We have to figure out how many moles, if we did want to react all of our moles of aluminum, how many moles of hydrochloric acid would we need? Well, we see the relationship is 3 to 1. 6 to 2, you reduce that down, is a 3 to 1 relationship. In other words, we need 3 times as much hydrochloric acid as we have aluminum, just based on these two coefficients here. If you want to say 6 to 2, that's fine, but it's a 3 to 1 relationship. Okay, that means in order to figure out how much hydrochloric acid I need in moles in order to react 1.35 moles of aluminum, I need to multiply this by 3 to get that. Okay, so this is really the key point to be sure you understand. If you don't understand this point, follow it, and we're going to do it, a number of times in this problem set. So what I get is 4.05. So just stare at those numbers for a second. Be sure you understand them. If I need 6 moles if I need 6 moles of this to react 2 moles of that, that's 3 times as much hydrochloric acid as aluminum. Then if I put in this much aluminum, I need 3 times as many moles of hydrochloric acid, and that's 3 times as many moles of that. That's how much hydrochloric acid I would need. Now let's go down in the other direction. If I have this much hydrochloric acid, which is what I was given, and I want to react all of that, I'm going to need 1/3 that many moles of aluminum. Okay, again, it's a 3 to 1 ratio, or in the other direction, it's a 1 to 3 ratio here. So I'm going to take 0.13 and I'm going to divide it by 3, and I get 0.43. So I have 0.43, and that's moles of aluminum. Okay, so now we have all 4 of these boxes filled in. So we want to figure out which of these reactions could actually take place given how much of each of the reactants we were given. So we simply ask ourselves, do we have at least this many moles of each of these reactants in each of these situations? So the question is, do we have at least 1.35 moles of aluminum? Well, yeah, that was the number we were given. So yes, we have that. So I'm going to circle the Y. Yes, we have that much. The next question is hydrochloric acid. If we want to run this reaction, we need 3 times as much hydrochloric acid. Do we have at least 4.05 moles of hydrochloric acid? Well, when we look down here, no, we don't even have close to that. We only have 0.13 moles of hydrochloric acid. So I got to circle a no for that. We don't have that much hydrochloric acid. Let's keep going, and then we'll draw our conclusions here. Do we have at least 0.13 moles of hydrochloric acid? Yes, that's the amount we were given, so the answer to that one is yes. And over here, do we have at least 0.043 moles of aluminum? Well, yes, we have a lot more than that. We have 1.35 moles. That's a lot bigger than this number. So yes, we have at least 0.043 moles of of aluminum here. So we look here and we say, yes, we have enough of each of these to run this reaction on the bottom. Okay, we have at least enough. We have exactly that much HCl, and we have well more than that much aluminum. So yes, we have enough to do that. On the top, however, we don't. We have this much aluminum, but in order to make all of that burn up, we would need 4.05 moles of HCl, and we already determined we don't have anywhere near that. We only have 0.13. So this reaction on the top will not work. So what you do is look at these 4 squares. The one that has the no in it, which is hydrochloric acid right here, that's our limiting reactant. It's the one we're running out of first. So we cannot run the reaction on the top. What we can figure out over here is, if that's the limiting reactant, the other one is the excess reactant. It's the one, when we run this reaction on the bottom, which is the one we said we could run, how much aluminum are we going to have left over at the end when we burn up all of the 0.13 moles of hydrochloric acid that we were given? How much aluminum are we going to be left with? Well, we know we were given this much, and we actually burn up this much in this reaction. We use this much. We react, I shouldn't say burn up, but we react this much. So let's just do a simple subtraction problem. And you end up with 1.31 approximately. I'm just rounding this off, 1.31 moles. And that's called excess reactant. That's excess aluminum. That's how much will be left over after we've done this whole thing. Okay? So that's how you determine what's limiting and what's in excess. Now, what we want to ask is, how much of these products over here can we produce? We know this reaction won't run. This one will. I did kind of a poor job of writing these things. I should have written them down lower. So I'm going to write a box here and a box here, which is going to correspond to this reaction right here. These two we can't use because this reaction doesn't work. We don't have enough HCl. So how do you determine this? And this is actually not very hard. What it's saying is that for every 2 moles of aluminum we burn, we're going to get 2 moles of aluminum chloride. And what that means is it's a 1-to-1 relationship. Okay, I hope you understand that concept of ratios, 1-to-1. 2 to 2 is the same as 1-to-1. For every mole of this you burn or react, you get 1 mole of this. If you react 2 moles, you get 2 moles. If you react 25 moles here, you get 25 moles here. It's a 1-to-1 relationship. So what that means is I can simply look at the reaction that works, the one on the bottom, and I can say I'm going to react 0.043 moles and that's a 2 there. So over here, the 2 is going to be 0.043. It's a 1-to-1 relationship. Okay? Good. Now, how about hydrogen? Well, you can pick whichever one of these you want to use to help you do this. But what this says is that for every 6 moles of HCl I react, I'm going to get 3 moles. I'm going to get half as many moles. If this number were 600, this number would be 300, and so on and so forth. It's half as many moles of this as this. So we look at how many moles that we reacted here. It's 0.13. If you divide that by 2, half of that number is going to be 0.065 moles. And that's how many moles you will get of H2. So that's how you do a limited reactant problem. So now we're going to do 5 more, and hopefully by the end of the 6th one, they're gonna all make sense to you. Okay. All right. Let's keep moving on. Now again, to have done this properly, I don't know which of these 2 reactions is going to work, so I should have actually put a box down here as well. We don't know. Only one of these reactions will work. The other one will run out of one of the reactants first, okay? So let's go ahead and do this. So I've already computed the molar mass conversions here, and then I've converted the 22.7 grams of nitrogen into moles. That's 0.81 moles of nitrogen that we were given to work with, okay? These are what we're given to actually work with. So I'm going to plug that into the all nitrogen reaction. Assuming that I burn or react all of that, I get 0.81. And keep in mind, all these numbers are in moles, so I'm not going to keep writing unit of measure for mole. You have to be in moles to work inside of a chemical equation, okay? All right, so that takes care of that. I'm going to circle that because that's an actual number we know that we have. How about the hydrogen? Well, we computed the 3.4 grams using the molar mass conversion is 1.68 moles. So that means here in the all hydrogen, assuming I use all the hydrogen that I have, I'm going to use up 1.68 moles. And I'm going to circle that because that's an actual number that I know that we have. Now we have to go ahead and figure out these 2 right here. So this is saying that for every mole, every 1 mole, and if you'd like you can write a 1 there, for every 1 mole of nitrogen we use, we're going to need 3 moles of hydrogen in order to make this reaction work. So the number that goes there is 3 times this number, which is 2.43 moles. If I want to burn all of the nitrogen, I'm going to need 3 times as much hydrogen, 2.43 moles. We go down here, we do the same thing but in reverse. I need 1/3 as many moles of nitrogen as I have of hydrogen. So if I have this much hydrogen, I'm going to need 1/3 that much nitrogen right there. Okay, again, you're just using the ratio of the coefficients in front of each of the reactants, and you just reduce those down to the lowest terms, which is 3-to-1 in this case. So 1.68 divided by 3 is going to give us 0.56. So in order to react all of the hydrogen, I'm going to need 0.56 moles of nitrogen. All right, so here we go. Now we're ready to go around and do our yes-no matrix here and see which one works. So do we have at least 0.81 moles of nitrogen? Well, yes, of course, that's what we were given. That's why we put that there, okay? So that's a yes. Okay, do we have at least 2.43 moles of H2? No, we don't. We only were given 1.68 moles, so we do not have at least 2.43 moles. So that's the one that's going to run out first. We would need 2.43 to make all of this react. We don't have that much. Okay, we'll just go ahead and continue and finish it anyway. 1.68, yes, that's what we were given of H2. So yes, we have 1.68 moles of H2. Do we have at least 0.56 moles of nitrogen? Yeah, we have 0.81 moles. That's more than 0.56. So we have at least 0.56 moles of nitrogen. So we put a yes there. So again, our no is in the hydrogen column. So that means hydrogen is the limiting reactant. It's the one that's going to run out first. And now we can figure out what our excess is. It's always the bigger number minus the smaller number, okay? We were given 0.81 moles of nitrogen. We only had to use 0.56 moles to make this to use up all the hydrogen. So you do a little subtraction problem and you get 0.25 moles, and that's excess nitrogen. Okay, and there you go. So which reaction did we say would work? It's the one in the row that has two yeses, just as it was up here in the row that has the two yeses. It's in this row that has the two yeses. So this is the reaction that's actually going to work. This one can't work up here. We don't have enough hydrogen. Okay, so now what you do is you just simply say, how much NH3 ammonia do I have here? Well, you can use any combination of these ratios with either 2 to 3 or 2 to 1. It's much easier to use 2 to 1. I'm going to end up with twice as many moles of ammonia as I have moles of nitrogen, because that's a 2 to 1 relationship. So if I simply take this number and multiply it by 2, that tells me how many moles of nitrogen I'll end up with, and that's 1.12 moles. Now, I know the instructions at the top said convert it back from this into grams. We're not going to do that just to save time. It's just simply another molar mass conversion. It just takes time. We really want to focus on the limiting reactant part of this. So once we get to moles, we're going to stop. So I'm not actually following the instructions that were on the top of the page. If you want to do that for extra practice, you're welcome to. Okay, we're going to move on. And we're going to go on to the next two problems. And now I give you problems where I don't draw the boxes for you, okay? But I'm going to do them just by hand. I'd recommend you do them until you get really comfortable with this process, okay? So I have silicon tetrachloride here. So I'm going to put a box here, a box here, and then one underneath the water. By the way, there should be an arrow right here, which I muffed and didn't put in there. So go ahead and be sure that gets put in there. It's right here. It's right in between the water and the silicon dioxide there, okay? So I'm going to draw a box here and a box here. And it's arbitrary which one you make the all, whichever, okay? I'm going to make the one on top, the all SiCl4. And the one on the bottom, the all H2O, assuming that I use all the H2O in this one, okay? All right. Now, I've already done the conversions, the molar mass conversions, just to save some time, and then converting from grams. We were given 53.7 grams of SiCl4. We're converting that into moles. We get 0.32 moles. So I'm going to go ahead and put that up here. If we used up all of that we were given 0.32 moles. There it is, okay? And I'm going to circle that because we know we have that much SiCl4. Now, what about the H2O? There it is right there. It's 0.74 moles is how much that 13.4 grams will convert into. So that goes in the water column, the H2O column, 0.74. And we were actually given that amount, so I'm going to circle that. Okay. Now I've got to figure out the others. Well, I need twice as much water as I do silicon tetrachloride, okay? It's a 2 to 1 relationship. So what I do is simply take this number and multiply by 2 to get this number. So I take this number and multiply by 2 to get this number, and that's going to give you 0.64. Okay, Same thing in the opposite direction. We have twice as much water as the SiCl4, so this number is going to be twice this one, and I go ahead and divide that, and I get 0.37 moles of SiCl4. Okay, now we go around and we do our yes and no. Do we have at least 0.32? Yes, that's what we were given. That's what we were given over here. Okay. That's what we were given over here. Yes, so that's a yes. Okay, do we have 0.64 moles of water? And the answer is yes, we have 0.74 moles of water. We were actually given that much, so we do have at least that much. We have more than that much, in other words. So that's a yes. Next, do we have 0.74 moles of water? We just answered that, yes. Okay. And then for this one to react, you need half as much. In order for this to fully react, you need half as much of the SiCl4. Do we have at least 0.37? And the answer is no, we only have 0.32. So that's a no. So again, learn how to interpret this yes, 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 no. What it means is that this, whichever column the no is, that's the limiting reactant. That's the one that's going to run out. Okay. And the reaction that's going to work is the one that has yeses in both. It's the row that has two yeses. So the all Cl4 is the one that's going to actually work. So I'm just going to draw a big rectangle around this whole thing like that. Okay. And I'm going to draw a couple boxes here because this is the reaction that will work, okay? We don't need boxes down here because this reaction doesn't work. We don't have enough SiCl4 to make this work. So we're going to put two boxes there. And before we figure out the products here, let's figure out the excess. So it's always the bigger minus the smaller. We were given this much. For the reaction that actually works, we only needed 0.64, but we were given 0.74. So you do the subtraction and you get 0.10 moles of excess H2O. Okay, so one of them's limiting, one of them's going to be in excess. Okay, let's finish off by figuring how many moles we end up of our products. Well, we have 1 mole of silicon dioxide, 1 mole of SiCl4, so that's a 1-to-1 ratio. So if you put in 0.32, you're going to get out 0.32. Okay, and finally we have 4 moles of HCl, and you can use either of these relationships, 4-to-2 or 4-to-1 for this one. Let's go ahead and just use the 4-to-1. I'm going to get 4 times as much hydrochloric acid as I put in, 4 times as many moles as I put in SiCl4. So you multiply that number by 4 and you get 1.28 moles of hydrochloric acid will be produced. And that takes care of that. That's how you do that problem, okay? So study this, or even write it out a second time on another piece of paper. Be sure you're clear how we're doing these steps, okay? Here we go. Let's keep rolling. Try to get this done in under about 35 minutes, okay? Maybe 40. All right, here we go. So we have AU2S3. So I'm going to draw a box here. Box here. Okay, we don't know, I'm going to draw a box down here. We don't know where we're going to draw our product boxes yet until we see which reaction is going to work. Okay, so let's say we use up all of the AU2S3. Okay, and down here we're going to say, what if you use up all of the hydrogen? Okay, I've already done the conversions over here. So let's go ahead and do that. So how much AU2S3 were we given? We were given, if you convert the 304.2 grams into moles, that gives you 0.62 moles. So this is 0.62. I'm going to circle that because that's an exact amount we know we were given. For the hydrogen, 18.8 grams converts to 9.3 moles here. So down here, again, we go to the hydrogen column and all the hydrogen, assuming we use all of the hydrogen we were given. That's an exact amount we were given, so I'm going to circle that. Now we figure out these. Well, I need 3 times as much hydrogen as I have of the AU2S3. So I'm going to go ahead and multiply this by 3, and I end up with 1.86. Okay, excuse me there. So all of the hydrogen is there, and now how much of the Au2S3 gold sulfide would that translate into? You need 1/3 as much gold sulfide as you have hydrogen, so divide this number by 3 and you get 3.1 moles. That's the ratio. It's always a 3 to 1. So this is 3 to 1, this is 3 to 1, this is 3 to 1. Okay, it's just the exact same ratio. Now we go around and do our yes/no matrix here. Do we have at least 0.62 moles of gold sulfide? Well, yes, that's how much we were given. That's why it's circled, so yes. Do we have at least 1.86 moles of hydrogen? Well, yeah, we were actually given 9.3 moles, so we have way more than 1.86 moles. So yes, we have plenty of hydrogen to make that reaction work. Down here, we were given 9.3 moles of hydrogen. Now, do we have at least, if we want to burn all that up, we need 3.1 moles of gold sulfide. Do we have at least that much? No, we only have 0.62 moles, so that's our no. Okay, so the reaction that's going to work is the one in the row with the 2 yeses, so I'm going to put a big box around that one. That one works. And that means I can go ahead and draw my boxes down here to figure out how many moles of products, and if I were so motivated, I could go on and figure out how many grams of each of these products it would produce, but we're not going to do that in this assignment. Okay, so what's the limiting reactant? It's the one in the column with the no, so it's the Au2S3. So this is limiting. It's the one that's going to run out first. Okay, and then we have excess hydrogen quite a bit. Okay, and just do a little quick calculation here, and it's 9.3 minus 1.86. That means we're going to have 7.44 moles of excess hydrogen. That's hydrogen that's left over that goes unreacted. Okay, and now we can come on over here and figure this one out. Well, we're going to get gold. What we're doing is producing pure gold out of this compound over here. We're going to get twice as many moles of pure gold as we have of this compound. So since we had 0.62 moles of Au2S3, we're going to have twice that many moles of gold, and that's going to be 1.24 moles of pure gold. Over here, it's easier to use this rate relationship. It's 3 to 3. Remember, that's a 1-to-1 relationship. However many moles of this I put in, I'm going to get that same number of moles out. So what we actually put into this reaction was 1.86 moles of H2. So we're going to get out 1.86 moles of hydrogen sulfide. Okay, and that takes care of that problem. All right, let's finish up with a couple more here. All right, so this is a simpler reaction than some of the ones we've been dealing with. We have nitrogen and oxygen here, okay? And they're going to produce nitrogen dioxide. So I did the molar mass conversions are here. Converting the grams, 32.2 into moles of nitrogen, you get 1.15. And converting the 43.5 grams of oxygen here, using the molar mass ratio, you get 1.36 moles of O2. So go ahead and draw your boxes. And at this point, if you don't have to draw the boxes, it's meant as just kind of a device to help you remember how to do these problems, just to give you a kind of a visual aid. But I would recommend doing it until you're really, really proficient at this, okay? We don't know where we're going to draw the box here. We don't know which of these reactions is going to work. We're going to make the top one the all N2 reaction, assuming we use up all of our nitrogen. And we're going to make the bottom one the all oxygen reaction, assuming we use up all of our oxygen. So let's go ahead and put in the numbers. We have 1.15 moles of nitrogen, so we're going to assume that we use that all up here. We're going to circle that because we know we're given that much. We have 1.36 moles of oxygen. We're going to put that in the oxygen column here under the all O2, so 1.36 moles of oxygen. And now we just do our little calculation. It's a 2-to-1 ratio of oxygen to nitrogen. You know, write the 1 there just to emphasize that. 2 to 1, so it's you need twice as much oxygen as nitrogen, so that's going to be 2.30 here. And you need half as much nitrogen as oxygen, so that's going to be 0.68 moles of nitrogen in order to make that reaction work. And now we go around and do our yes-no matrix here. We know we have 1.15, that's what we were given. Do we have at least 2.30 moles of O2? Yes, we do. We have, no, we don't. We were only given 1.36 moles of O2. We do not have 2.3. We don't have enough to react all of the nitrogen, so that's where our N is going to go. Okay, this one I should have circled, and we know we have that much oxygen, 1.36 from right there. And do we have at least 0.68 moles of N2? Yes, we have more than that. We have 1.15, so that's a yes. So our no comes in the oxygen column. So the oxygen is the limiting reactant. And we end up with 1.15 minus 0.68. And that gives us 0.47 moles of excess nitrogen. So 0, I'll just do a little subtraction there, 0.47. It's always the bigger minus the smaller moles of excess nitrogen. Okay, so the reaction that's going to work is the one in the row with the two yeses. There are the two yeses, so I'm going to go ahead and draw a box like that. And that means my product box is going to be down there. And I'm going to get as many moles of nitrogen dioxide as I have moles of oxygen. It's a 2-to-2 relationship. You just find the easiest relationship to convert. That's that. So if I had 1.36 that I put in, I'm going to get 1.36 of this out. Okay, and that's how you do that. All right. Okay, one more to go. Okay, here we go, last problem. So we have a reaction, a combustion reaction of C2H6O. That can go by a number of names, but ethanol is one of the more common ones. What you're doing is burning that in oxygen, and you're producing what all hydrocarbons, carbohydrates produce, which is carbon dioxide and water. Okay, so let's go ahead and draw our box. Okay, we're going to react all the ethanol. And one reaction where we react all of the oxygen. Okay, I've already done the conversions. We were given 78.1 grams of ethanol, and we convert that to moles, and we get 1.69. So we put that in the ethanol column and in the all ethanol row. Oxygen, did the conversion from 43.5 grams, you get 1.36 moles of O2, so that's in the oxygen column and in the all oxygen row. Circle those because those are actual givens. We were actually given that much. Now we figure out the other two. Well, we need 3 times as many moles of oxygen as we have moles of ethanol if we want to react it completely. So we do a just a little multiplication, and that's going to be 5.07. Let me check that. I want to do things in my head here. That looks good. Okay, and then again, it's a 3-to-1 ratio in the other direction, 3 of oxygen for 1 of ethanol, so you have 1.36. And so we're going to divide that by 3, and that's 0.45. With some change left over, that's okay. We'll go with 0.45. Okay, so there we are. So again, let's go around, do the matrix. So yes, we know we have that much. That's how much we were given of the ethanol. Now, do we have at least 5.07 moles of O2? And the answer is no. We only have 1.36 moles. So if we try to react all of this, we're going to run out of oxygen. In other words, this won't completely burn. This will run out of oxygen before we burned all the ethanol. So that's a no. Down here is a yes. Anything circled is a yes because that means that's how much we were given of oxygen. And then the last one, we just go ahead and do it anyway. 0.45, do we have at least 0.45 moles of ethanol? Yes, we have 1.69. So yes, that's a definite yes. We have at least that much. So both of the yeses are in the bottom column. That means that's the reaction that will actually work. Okay, our limiting reactant is the one with the no in its column, so oxygen is the limiting reactant here. It's the one we're going to run out of first. And that means we have 1.69 minus 0.45. And that's going to give us 1.24 moles of excess ethanol that will not be burned. Let's go ahead and write this. Okay, there you go. Now let's figure out how much of the products we'll get out of this, and we'll be all done for the evening. Or afternoon if it's Sunday for you. Okay, so what do we look at here? Well, water is the easiest one to do. There's 3 moles of water for every 3 moles of oxygen. So that's a 1-to-1 relationship. For every mole of this, you get the same number of moles of that. So 1.36, 1.36. Okay, and then carbon dioxide, there's twice as many moles of CO2 as there are moles of ethanol. So it's a 2-to-1. So if I have 0.45 moles of ethanol, I'm going to have twice that, or 0.90 moles of carbon dioxide. Okay, and that's how you do those problems. So I'd like you to come into class on Monday morning with this sheet done. It will be collected at the beginning of class, and I'll check it off and give it back to you maybe even the same day or no later than Tuesday. Okay, have a good weekend, and just spend a little time on this and get these down. Bye-bye.